Hello students, warm welcome to all of you at AriserTalent. How are you all? I hope you are doing amazing. So, we will discussed about the chapter that is of the chapter number 2 of our physics, that is about the magnetic effect of the electric current. So, in magnetic effect of electric current, in our previous lecture, we had a discussion about magnetic field lines. So, we have discussed how the magnetic field lines will be formed in case of a current carrying conductor, in case of the circular coil, and in case of the solenoid. So now today we are going to discuss about the expressions that how you will find the magnetic field strength at that particular point. So today we are going to discuss some of the important formulas, but the formulas I am writing here is only for your competitive point of view. It may not be asked in your CBSE exam, it will only for your competitive purpose. So by substituting the values, you can find the value of the magnetic field strength there. So today we are going to start our discussion with magnetic field formula. So in this category, we are basically finding the magnetic field due to current carrying conductor . Secondly, we will find an expression for the magnetic field due to current carrying coil . And thirdly, we will find a formula to derive an expression for magnetic field due to solenoid. So, we will learn about three basic formulas here and try to determine the magnetic field in each case. So, the first one will be the magnetic field due to the current carrying conductor. Second one is magnetic field due to the circular loop. And the third will be the magnetic field due to the solenoid. I know these terms has been cleared to you because we have drawn the magnetic field lines of all these parameters. Now, firstly, we will write an expression for the magnetic field due to the current carrying conductor and try to find out the direction in this case. So, firstly, let's start with our first topic, that is about the magnetic field due to a current carrying conductor, which is basically a straight conductor you have. So, starting with the first expression, we have magnetic field due to a straight conductor. Now, for calculating the magnetic field due to the straight conductor, here I am assuming that this is a conductor. This is the conductor I have. I am assuming that this conductor is named as PQ. This conductor is named at PQ, and at a particular point in the field, I have to determine the value of magnetic field strength at the point A. What I have to do? I have to determine the magnetic field strength at point A. So, what I am assuming here? I am saying that our conductor is PQ. So, here PQ is a conductor of length L. This PQ is having a length L. So, this is a conductor I have and this is having a length L. Now, you have to determine the magnetic field at point A. So, what we have to determine? We want to determine the magnetic field at point A. This we have to determine. If I have to determine the magnetic field at point A, I am assuming that it is making an angle theta 1 and theta 2 with this A. So I can say that this angle is our theta 1 and this angle is our theta 2. So these are the two angles I am getting here. So magnetic field is usually denoted by the symbol B, and magnetic field strength at a point A can be given by the formula mu 0 I upon 4 pi r sine theta 1 plus sine theta 2. So this is the formula for magnetic field due to a current carrying conductor. And I will be the value of the current flowing in this conductor. Now, here B is our magnetic field strength. B is our magnetic field strength. Mu naught is actually the permeability of the medium. So mu naught is equal to permeability. It will be the permeability of free space or medium, we can say. I is the current flowing in the conductor. I is what? I is actually current flowing in conductor. And what will be the R? R will be the distance of this point from current carrying conductor. So I can mention here this will be our R. So R is equal to distance. Theta is our angle. And 4 pi will be the constant and the value of pi will be 22 upon 7. That will be 3.14. Now, what will be the unit for calculating the magnetic field? The unit for calculating the magnetic field is Tesla. The unit for determining the magnetic field, it is a very important unit because you have to put a unit after every quantity you are writing. So the unit of magnetic field here is Tesla, and if I am going to find out the value of this mu naught, so the value of the mu naught came out to be mu naught is equal to 4 pi into 10 raised to the power minus 7 Tesla ampere per meter. So this will be the value of permeability, and for solving the numerical problems you have to learn this value. The value of mu naught will be 4 pi into 10 raised to the power minus 7. So due to the straight current carrying conductor, I can derive here the expression that is equal to mu naught I upon 4 pi r sine theta 1 plus sine theta 2. And this formula you have to keep in your mind for solving the numerical problems. So just copy this part from here so we can proceed to the next part. Now, if I am assuming that this conductor is of the infinite length, we do not know the length of the conductor. Firstly, we have assumed that the length of the conductor is L here, but now we do not have any idea about the length of the conductor. So, in case of infinitely long conductor, the magnetic field value has been changed. So, if conductor is of infinite length, so we cannot determine the value of the length here, and the angles will also be going to change in this case. So, in case of infinitely long conductor, B came out to be mu naught I upon 2 pi r. So, this is the formula for determining the magnetic field strength due to a infinitely long conductor. Again here, mu naught will be the permeability of free space. It will be the permeability of, we can say, vacuum. and it is equal to 4 pi into 10 raised to the power minus 7. So this will be the expression you are getting here. So this is the magnetic field due to an infinitely long conductor. Now, this is about the magnitude we have determined, but also we have to determine the direction of this current. So, the direction of this magnetic field is basically given by two important rules. The first rule is Maxwell's corkscrew rule, and the second rule is about the rule that we have already discussed about the right hand thumb rule. So, let's move to the direction we want to determine here. So, the next thing is about the direction of the current or the direction of the magnetic field in both the cases. So, direction of magnetic field and current is basically given by the two important rules, and these two important rules are first Maxwell's corkscrew rule, and the second rule is our right hand thumb rule. And now we are determining the current carrying, we are assuming the current carrying conductor and try to find out the direction of the current here. So firstly, we will discuss about the Maxwell's corkscrew rule. So let's start with the Maxwell's corkscrew rule. Now what corkscrew rule signifies here? You have to assume that you have just holded a corkscrew in your right hand. So I have just taken a corkscrew here and I have just put it in, I have just holded it in my right hand. Now in this corkscrew you can see that you have to align the axis of the current and the axis of the magnetic field in such a way that current always precedes the magnetic field. It means the current will always be in the forwarded direction. So the direction in which the cork is screwed to be opened is said to be the direction of the magnetic field. So the direction of the magnetic field can be analyzed from the right hand cork rule. So what you have to do, you have to just coincide this screw with the direction of the current, and if you start rotating this, the rotation will give you the direction of the magnetic field. Suppose this is the screw I have. If I am rotating it like this, if to pack it, if I am rotating like this, then this rotation will going to give you the direction of magnetic field. And to open this, if I am rotating it in anti-clockwise direction, it is opened in the anti-clockwise direction. So this direction will going to give you the magnetic field. So what you have to do in Maxwell's corkscrew rule, in our first rule, that is Maxwell's corkscrew rule, what you have to do, you have to, so we are imagining a right-handed corkscrew. You can imagine a right-handed screw placed coincides with the current, such that its rotation always advances the direction of the current. It rotates and advances direction of current. If it is advancing in the direction of current, then rotation will going to give you the magnetic field. So, direction of rotation will be the direction of magnetic field. So this will give us the direction of the magnetic field. So for understanding this system, I am just drawing the diagram here. What you have to do, you have to advance it in the direction of the current. It means it always advances the direction of the current. So in the direction in which the screw is rotated will give you the direction of magnetic field here. So for this, I'm just drawing a simple picture here so you can easily understand this. So this is our screw. So this part will give you the direction of current. This part will give you the direction of current. And if screw is rotated in this part, if it is rotated in this part, it will give you the direction of magnetic field. So this is all about the Maxwell's corkscrew rule. Our second rule is a right hand thumb rule, which is a very easy rule, and we have also discussion about it earlier. So what right hand rule specify that if I capped my right hand in such a way that I am going to curl my fingers, then the thumb will give you the direction of the current, and the rotating and the curling of the fingers will going to give you the direction of the magnetic field. It means if I am going to curl the fingers of my right hand in such a way that it is curled inward, then inward will be the direction of magnetic field and upward will be the direction of the current. So if I am assuming that this is my current carrying conductor, this is my current carrying long conductor, and I am holding it in my right hand. If I am holding it in such a way that it will be fingers are curling inwards, then thumb will give you the direction of current and curling of the fingers will give you the direction of magnetic field. But if I am holding this conductor like this, suppose we are holding it like this, it means like this. If I am holding this conductor like this, you can see that my fingers are curling outside. Fingers are curling outside, so what will be the direction of current? The thumb will give you the direction of current in the downward side. So this is how the right hand thumb rule works. So second rule is our right hand thumb rule. Now, right hand thumb rule states that curling of fingers will give you the direction of magnetic field and thumb will going to give you the direction of current. Thumb will give you the direction of current. So this is what? This is our right hand thumb rule. Now, if you are showing the current in the direction, then you have the two symbols to represent whether the plane is in upward or downward direction. So we are using here two symbols. So what I will do here, I am just removing this part so I can draw right hand thumb rule here. So this will be our right hand thumb rule. Now, if I am drawing the current carrying conductor like this, this is our current carrying conductor and we are just holding it with our right hand. So, this is how I have hold the conductor. I have just used my right hand and I am holding the conductor like this. I am just holding the conductor like this. It means the curling of the finger is inwards and thumb is pointing in the above direction. So this is the value of current I have. The curling of the fingers is in inward direction and it will show you the magnetic field strength. Then for having the inward direction, it means the plane is in inward direction. What we will do? We will represent the plane with the dot. We will represent the plane with the dot. In the similar picture, what I am doing, I am just holding the conductor like this. It means from the backwards. So what we will do? We will hold the conductor like this and the thumb will be pointing outwards. So this is how we have hold the conductor. Now, what I have done, I have just hold the conductor in such a way that in the beginning part, I have hold the conductor that my fingers are inwards. Now, my fingers are outward. Fingers are outward in this case. So this thumb is pointing downwards. So this thumb which is pointing outwards, it will show you the direction of current. This will be current here. And it is showing the curling of the fingers not in inward direction. It is showing in the outward direction. So we can represent it by the cross, and cross P will give you the outward direction. So this is how the right hand thumb rule actually works. If you move the fingers inside, the thumb will point in the upward direction. If you curl your fingers outside, the thumb will give you the direction of the current, which is downwards. So this is how the right hand thumb rule works. So in our today's lecture, we have a discussion about magnetic field due to a straight current carrying conductor. And we have also determined the formula for it, which is very important for solving the numericals problem. Now in our next lecture, we will deal with magnetic field due to a current carrying coil and solenoid. So this lecture is over here. Thank you so much and have a nice day.